So for our function f of x, we've already found the domain, the symmetry of the function, namely we proved it was odd, and we found the first and second derivatives. So now we want to go find the critical values, and we want to find both the first and second order critical values. So I'm going to do that right here at the top of this page. And I'm going to add in a table later, so you want to leave yourself some space. In later sections of this course, I'll actually make that table ahead of time. But if you're watching it in winter of 2019, you'll have to draw it yourself with rulers. All right, so step 4, we want the first and second order critical values. Okay. So first order critical values, let's start with those. The first order ones would be where f prime does not equal 0, so let's do first order over here. That would be where f prime is equal to 0 or f prime does not exist. All right, f prime equals to 0, it'd be, remember that the first derivative is this function. So if it's equal to 0, that will mean that the numerator is equal to 0. And if it does not exist, that'll be the denominator equals 0. Okay, so this will be 10x to the fourth minus 30x squared equals 0. This one right here. That would be, let's see, I can take a 10x squared out. That'll leave me x squared, take away 3. All right, well, two things multiply to 0, so either 10x squared is equal to 0 or x squared minus 3 is equal to 0. This would mean x squared equals 0, which means x equals 0. Right? You divide by 10, then you take the square root of both sides, but you don't need to worry about plus or minus because it's 0. This would be x squared equals 3, and that would mean x equals plus or minus the square root of 3. All right, so there are our first order critical values right here. And I know what you're thinking. You're thinking, what about the other side? Well, the other side would be x squared minus 1, quantity squared equals 0. That would mean that x squared minus 1 is equal to 0. Take the square root of both sides. That would mean x squared equals 1, which means x equals plus or minus the square root of 1, which is mean x equals plus or minus 1. However, that should be setting off little bells in your head because in step 1, we showed that plus or minus 1, actually it's the exact same calculation, cannot exist for this function. So they are not in the domain. So we don't have to worry about those. So not in the domain. Right. So they'll already be tossed out, but that's because they're part of, not in the domain of the function. All right, so that's the first order critical values. Now let's find the second order critical values. Okay, well again, that would be where f double prime is equal to 0 or f double prime does not exist, right? The second derivative. Okay, the second derivative had, when we simplified it, had a numerator of 20x cubed plus 60x. Which, by the way, if you didn't simplify it then, you'd have to do it now because you would want to set that entire numerator equal to 0 to solve. Right? All right, so that would be 20x cubed plus 60x equals 0. These are both factorable, so I'll take 20x out, leaves me x squared plus 3 equals 0. That means either 20x is 0 or x squared plus 3 is equal to 0. This would mean x equals 0. And this would mean x squared equals negative 3, which is impossible. In other words, x is plus or minus the square root of negative 3, and that's not real. So we're not going to worry about that one. So there's our critical value right there. This one would happen, if you remember the denominator, it was x squared minus 1 cubed, and that would be equal to 0. Well, again, we don't have to worry about that because that'll be x, it'll be the same steps as before. X squared minus 1 equals 0, x squared equals 1, x equals plus or minus 1. And that's not in the domain. So the only second order critical value we have is 0. Okay, so this gives us our intervals. So we're going to combine together the domain along with the critical values. So when you're looking at your intervals, you want to use the domain and the crit values. All of them. Right? Okay, so, and again, if you don't have this table, I'm going to post this page of notes so you could print this so you could get the table without having to use a ruler, or you can just use a ruler, either one. So you start off at the beginning of your domain, which was negative infinity, and you go until the lowest of your critical values and or the things you can't have, which would be, let's see, there's negative 1 here, there's 0, and there's negative square root of 3. Negative square root of 3, that's the lowest, because that's about 1.7. Then I'm going to go from negative square root of 3 to negative 1. Oh, I'm worried that looks like the square root symbol instead of a negative. Let me just make sure that's very clear. That's a square root, there's a negative in front of it. Then I'm going to go from negative 1 to 0, right, my next critical value. Then I'm going to go from 0 to 1, right. Then I'm going to go from 1 to the square root of 3, and then I'm going to go square root of 3 to infinity. There are my intervals. Now I need a number in every single one of these areas. So these ones are easily, negative 0.5, 0.5. Between negative 1 and negative 1 point, let's double check that real quick. Let me pull up Desmos. I click Start Graphing, and then you can grab a calculator as well. Either way, but we just need a decimal approximation of the negative square root of 3. Or actually just the square root of 3. SQRT of 3, and it's about 1.732. Okay, so I need a number between negative 1 and negative 1.732. So I could do negative 1.5, that would work, and I'll do 1.5 over here, and then anything between negative 1.7 and negative infinity. So how about negative 2 and 2? Or 5 and negative 5, or anything you like. Sorry, that was off screen. I apologize. So the easiest ones are the ones on the end because there's infinitely many numbers. There's always infinitely many numbers, but not pretty ones. Okay, so now I want to know whether my f prime is positive or negative in each of these. And then that'll determine whether my function's increasing or decreasing. Now, there's an easy way to do this and a hard way to do this. Because we have to test so many values, it's kind of easier if you put in your functions. So you'll notice I went to Desmos, and I'm going to put it in my function. I'm going to label it f of x equals 10x to the third. I move my arrow to the right, and I'm going to divide that by x squared, take away 1. And a lot of what I'm doing is available to you down in the keyboard if you want to show the keypad. You can play around with the functions and stuff. But I did it all actually with keystrokes. Just using the caret symbol above the 6 for the powers, and using division and then arrows. Alright, so this is my function f of x. It's not really to the window that I want, so in case you're wondering. So we'll look at that a little bit more fine-tuned in a minute. I'm going to turn it off because I really don't need to see the graph right this second. Okay, so then I want the table. So what I'm going to do is I'm going to put in a table right here. And I'm going to put in my values. So I had negative 2, negative 1.5, negative 0.5, 0.5, 1.5, and 2. And what I can do is I can tell it over here, instead of y1, I can say, let's see if I can get this to work, f prime of x, and then to do 1, I just hit the number 1, close parentheses. And then it actually is finding the derivative and substituting the values that I want into that derivative for me. Right? So it is the same first derivative because I used f prime right there that we found earlier in part 3. And I can tell my signs from looking at this. Nice, huh? And you can make your calculators do this too. It's just a little clunkier on the calculator, I find. Alright, so that gives me my values. If you're wondering where it is on the calculator, it's in the table features, right? So you'd go to y equals, you would type the equation or the derivative in y equals, not the function, the derivative in y equals. And then you would go to the table and look for the numbers that we have. Okay, so where was f prime? F prime was positive 4.4 here, negative, 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 positive. Let me double check. Yeah, positive, negative, 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 positive. Okay, so what does that mean for my function? That means that it is increasing, decreasing, 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 increasing. That's the function. Or excuse me, the function is increasing or decreasing based on the derivative. All right, now we do the same thing with the second derivative. So let's go back to Desmos. And the thing that's nice about Desmos versus a calculator is that when you go to y equals in the calculator, you have to have that correct derivative found and put it in. For Desmos, you don't need to. You can actually just type. So f double prime, so I hit prime twice. So f prime prime of, and then I'm telling it x1, right, because it's specific x values. If you're wondering, can't I just type f prime of x and it'll give it to me? No, it'll give you a graph, but it won't give you the function. And you can see f double prime of x1, same test values, negative, negative, positive, negative, positive, positive. Right? So I'm going to go put those into my chart. So at negative, negative, positive, negative, positive, positive. That means that it's concave down. And then this would be concave down. This would be concave up, concave down, concave up, concave up. And there we have those. Okay, so now let's draw some pictures of what this is going to look like. And that'll help us. So I want a function that's increasing but concave down. That looks like this, right? It's going up, but the cupping, the bowl shape, is downward. I want a function that's decreasing and concave down. That's that. I want a function that's decreasing but concave up. So decreasing means it's going down, concave up means it's bowl shape up. So it looks like that. Decreasing but concave down again, so we've already seen that one. That looks like this. Decreasing concave up, we've seen that one before. It looks like this. Increasing concave up, that's new. We're going to go up, and we're going to be bowl shaped up. So that's what those combinations look like. All right, so that's step 5, right? This whole thing is step 5, this giant table. Right, so you find your test values, you find your f prime signs, then determine increasing, decreasing, your f double prime signs, determine concave up, concave down. Then you determine pictures from each of those. And then from there, you can figure out your local mids and local maxes for part 6. So it's really easy to spot on the graph. So you can see it went up and then back down, and this value's in the domain, so therefore we have, this will be step 6 down here, we have a local max at negative square root of 3 something. We'll figure that out in a second. All right, then let's see the next value. So from concave down to concave up, right here, but decreasing to decreasing, oh, but negative 1 wasn't in the domain. Right? Remember, negative 1 and positive 1 are not in the domain. So this one's not in domain, not in domain. So that can't be anything. And this one's also not in the domain. So that's not going to be a local min or max because they're not in the domain. Negative 1 and 1 are out. All right, then what about this value? It goes from being concave up to concave down. It's decreasing the whole time, see? So it's not going to be a min max, but it could be, and it is, an inflection point because it goes from concave up to concave down. This one happens, the local max happens more because it's going from increasing to decreasing, right? This one happens because it's going from concave up to concave down, and it's an element in the domain. So we have an inflection point at 0 something. And then let's see, concave down to concave up, that's not going to be an inflection point because it's not in the domain, so that's not going to be a problem. And then concave up to concave up, that's no big deal, but decreasing to increasing, That means we're going to have a local min, right, by the first derivative test at square root of 3 something, right? So I'm using, if you will, the first derivative test. From increasing to decreasing gets me local max. From decreasing to increasing gets me local min. None of the rest of them change, right? So those are the only local mins and maxes. The concavity only switches here, which is not in the domain, here, which is in the domain, and here again, which is not in the domain. So those ones are out. All right, the only other thing I would need is what are these points? So I would actually take the values and plug them back in the original, which you can do a variety of ways. So one thing I could do is I could actually make a new table in Desmos. So let me go to a table real quick. So I could say to it, hey, here's my values. So negative square root 3, and then 0, and then the square root of 3. And I'm just typing SQRT to do that. You actually could go to the keyboard in here and get these as well. And up here in the Y2, I'm going to highlight that. I'm going to say F parentheses X2. Sorry, X2. If I say X1, it's going to use the values from up above. And I can see this is negative 25.98. This is 0, and this is 25.98. All right, those are technically decimal approximations. If you want the more precise values, you'd actually have to go do a little bit of algebra. So this would be negative 15 square root of 3. This is 0. This is positive 15 square root of 3, which is also approximately the value we just saw in Desmos. And 25.98. 25.981, if you will. So 25.981 negative, and this would be 25.981 positive. All right, we're done with steps 4, 5, and 6.